Hi, my name is Tani, and thank you for taking your time to join us today. We're going to talk about a molecular biology technique called polymerase chain reaction, or PCR. So let me quickly show you the aspect that we're going to look at in a little bit more details along this presentation. We're going to talk about the purpose of the technique in the introduction and what PCR is used for. When it was discovered, how this technique was developed, followed by how does PCR work, its application. We're going to see some examples how PCR is applied in science and the advantages of the technique, the shortcomings of the technique, and the last aspect, but not the least, covering this presentation is the potential future applications or extensions for the PCR. Polymerase chain reaction is a method of amplification of DNA. That's it. The DNA is multiplied through a reaction. PCR has revolutionized the field of molecular biology because it's an easy process that allows you to make millions of copies of genes. Simple, it's a DNA duplication method. This technique is a copy mechanism for the genetic material. It's like a molecular photocopy. So, using PCR with a small segment of DNA, which you can call target DNA, it's possible to copy the DNA many times. In simple words, PCR is a rapid amplification of tiny fragments of DNA. Importantly in this technique is that it can recognize rare DNA sequences into extremely complex mixture of biological materials and also even a whole cell structures. So, once this sequence is identified, that could be from a single human hair or a saliva sample, then it can be amplified through PCR. That's why PCR is very important and highly used biotechnology for molecular biologists. What is PCR used for? Once amplified, the DNA produced by PCR can be used in many different laboratory procedures, such as diagnosis of genetic diseases such as cancers and tumors, detection of virus such as influenza virus or HIV virus, detection of bacteria. It also can be used to match organs donor with recipients in transplant programs, establish paternity. So the PCR has several uses, all very interesting, and the list doesn't stop here. PCR is also used for identify possible suspects whose DNA may correspond to evidence left in a crime scenes. It's used for the study of human evolution, detection of mutation, DNA clone of prehistoric biological materials such as mummies or dinosaur bones and extinct organisms. So its clinical application and laboratory uses is very valuable because PCR is an essential tool for scientists and many researchers that study genetic material. How PCR was discovered? Carrie Muslin was the creator of the PCR in 1983. He was working for one of the first biotechnology companies, and his role was to make short chains of DNA, the DNA synthesis. He stated he was been trying to think about an innovative way to analyze the mutations in DNA. However, he realized instead he has invented a method to amplify any regions of the DNA. The technique was published in 1987, and in 1993, Muslin and his colleague Michael Smith shared the Chemistry Nobel Prize for the PCR invention. 3 years before to receive the Nobel Prize, he wrote in the Scientific American, beginning with a single molecule of the genetic material of DNA, the PCR can generate 100 billion similar molecules in an afternoon. The reaction is easy to execute. It requires no more than a test tube, a few simple reagents, and a source of heat. Potential future applications or extensions of the technique. Since PCR was discovered in the early 80s, its use became routine to every labs to clone genes, diagnose disease, or identify genetic fingerprints. And many extensions of its techniques have been developed, and nowadays there are a significant number of them. PCR has yielded many generations of its methods and machines. So some of these extensions are endpoint PCR, multiplex PCRs, long PCR, quantitative, and digital PCR, to name a few. Quickly, we can have a look at this progress through these three techniques. For example, the endpoint PCR, it was the original version of the technique. It was created in 1983 and it's still very useful in labs. However, only provide relative and qualitative results. The quantitative PCR, it was developed in 1992, is also popular, and this technique has enabled quantitative detection and also provides an absolute result. And finally, the digital PCR or dPCR, more recently, has also become readily available. And compared to conventional PCR technologies, dPCR enables a more precise, sensitive, and reproducible target quantification. This evolution in PCR technique that has happened and is still happening over the years is essentially to solve specific problems associated with the technique or to improve its performance. Some of the improvements that researchers are looking for are speed, for decrease the wait time for results. They're looking for continuous flow to improve the heating and the cooling system of the technique. And they also wish simplicity, making possible run PCR tests in simple low-power device and reducing costs of diagnostic tests. So it's possible to see potential applications of the PCR in areas with poor medical facilities. The lack of resources, such as electricity, clean water, or transportation, would not be a barrier for the use of this developed technique. Due to the evolution, it's possible to achieve the sample preparation, amplification, and interpretation of the results done in the same device. And this is the future of the PCR. As Chow and his colleagues said, PCR extensions have found widespread application in medical diagnosis, environmental monitoring, and food safety. Here we conclude this presentation. Hope you had enjoyed it. Next, I'll reference on this topic, and thank you for watching.